Okay, everyone, welcome back to your next online class. My name is James. We're going to be talking about space science. If you couldn't tell that, it's kind of obvious. So we'll take off this space helmet here. The nice thing about space helmets is they usually don't mess up your hair too bad, apparently. A couple months ago, we talked about the life cycle of stars. We have a star, we have a sun, it exists. How does it work? How does it operate? How did it come into being and what's going to happen at the end of its life? Let's find that out. It's really fascinating. The history of our universe is explosive. We're going to learn about that. Hello to those who are saying hello in the Q&A box down there. I'm glad to have you all here with us. For those of you who are joining us newly, if you have questions, if you have something that you would like to add to the conversation, if I ask a question and I need answers from you, use the Q&A section down at the bottom or wherever that button is on your screen and add your stuff in. If I miss your question or your comment or your answer, I apologize. I'm never able to read everything out because we only have so much time and there's usually a lot of input from all of you, which I love. It's what makes these classes so enjoyable, for me at least. So hello to the 10 billion people that have said hello. All right, so we are talking about the life cycle types of stars and their life cycles. We're gonna start with this image here and we're gonna come back to it often because we're going to be exploring each step of what we're looking at here. But the general rough process is it starts with a stellar cloud with protostars. Don't worry, we're going to define each of these things. It starts as this cloud and it'll either turn into a small star or a large star. The small stars will eventually become red giants, which will become planetary nebula, which will become a white dwarf. If that initial thing turns into a large star, it goes on a slightly different path. It turns into a red supergiant, it goes supernova, and then it turns into either a neutron star or a black hole. If I just said a bunch of words that you don't understand, we are going to be defining each one of these in detail. So stick with me, and when we look at this same image in about 40 minutes, you're going to look at it and be like, oh, yeah, I understand that. I get that. Okay. All right. We are going to move on here. So it starts with this first step here. Whoop, go back a little bit. These stellar clouds. And it's called a nebula. It's a cloud of dust and gas. And it's just kind of hanging out there in space. And these things might be massive. They might be, light years across, huge, huge regions of space occupied by just kind of a loose cloud of dust and gas. This is a picture of one of them. It's called the Pillars of Creation. And you can see it's kind of like extending out there. What happened in the universe to create that exact formation? I don't really know, but it looks gorgeous. And those things are massive, massive, massive. Our entire solar system can fit easily into there many times. So these nebula have lots of hydrogen. Hydrogen gas is the simplest and most abundant element in our universe. So keep that in mind. It's going to be important later on. Just keep in mind, hydrogen, the simplest, there's a ton of it. It's your basic building block. This is your smallest Lego piece that you're going to use to build everything else. So here's some pictures of various nebula. Here's the Bat Nebula. Oh, that is so cool. Man, look at that. It's so cool. The Ring Nebula, you can see where they got the name for that. And here's the Crab Nebula. I don't know why they call it. That doesn't look like a crab to me. But hey, whoever discovered it named it the Crab Nebula. If you discover nebula, you can name it whatever you want. You're like, this is the Peanut Butter Nebula because I like peanut butter. Here's the Phoenix Nebula. It looks like a bird, phoenix rising, right? There's Nebula from Guardians of the Galaxy. That has nothing to do with this. It's just we're talking about nebulas, and so she has to be mentioned. Here's the Seahorse Nebula. Looks like a seahorse. That's really cool. Okay, so it starts as just this giant cloud. Lots of hydrogen in there, and it starts to clump together. Within a few 100,000 years of this stuff just kind of sitting out there, stuff in space likes to come together. It has gravity. Anything that has mass in space has gravity. So even if it's just, you know, some helium over here and some hydrogen over here and some hydrogen over here, it's going to be kind of drawn to each other just a little bit. It has some gravity. So give it hundreds of thousands of years and it starts to come together and it starts to spin, right? It's going to come together and kind of pass itself and kind of start spinning around itself. And this starts to create pressure. This starts to create, stuff starts condensing in the middle into a sphere because spheres are just the natural shape it's going to like to take, physics. And it starts to heat up. If you take your hands, I've said this many times in my past seminars, take your hands, put them together, rub them together, and you start to feel heat, right? So now take tons and tons and tons of gas and have that gas rubbing together as it's moving and spinning around itself, and it generates heat. So that core of that thing starts to heat up to like 2 million degrees Celsius, not even Fahrenheit. So it's like super hot, guys. That is what you call a protostar, a young star, an early star, the first kind of star. Before we move on, I'm going to check in the Q&A section. Gerard asks, is our sun a red giant or a supergiant? Neither yet. It will eventually become a red giant, not a red supergiant. And we'll talk more about that in a little bit. Hi, Shanna, welcome. I understand that you got here a little bit late. We're talking about the life cycles of stars. Jump in where we are now. You didn't miss a lot. You're going to learn even more. All right. And Alex says, we've actually seen black holes with our own eyes, and we have actual pictures of them. You are right, Alex. I'm so glad you mentioned that. I have that picture later on. Stick around. Okay. All right. Oh, and Katya's asking, did you get the drawing that Rusty drew for you? Yes, I love it. Thank you so much. I love that there's people in this class that were here in the last class. There's a continuity. Well, so what happens to this protostar? Here is an artist's rendering, an artist drawing of what a protostar might look like. You can see there's that glowing ball in the middle, and there's just a bunch of junk around it. This is the gas and dust starting to come together, starting to condense, starting to clump up. And it's going to take millions of years, many millions of years for that to kind of sort itself out. And it's going to be messy. It's really messy for a while. Here's an actual photo from a space telescope of a protostar being formed. It's actually two. You can see two clumps here. It is not uncommon for a star system to have two or sometimes even three stars at the center of it. Our own sun, our own solar system is a one-star system, but most of us have probably seen Star Wars. We're familiar with the planet of Tatooine. And there's that iconic scene of Luke Skywalker standing there, staring off into the sunset as the twin suns, the two suns of Tatooine are setting. That is a common sight in the universe. That is not unrealistic. It's very normal for a planet to have two stars. Like this system here, it will have two stars when it's done forming, 1, 2. Unless they come and collide together and one eats the other, which could happen. Forming planets and forming stars is a messy business. Here's another actual image. This is a 3-star system. So a 2-star system is called binary. Binary meaning there's 2. And a 3-star system would be called a trinary system. And you can see there's one big one here, and then there's 2 smaller ones there. Those are orbiting each other like this, and the big one is orbiting outside of those 2. Trinary star systems are not all that uncommon either. The closest other star system to us after our own sun is the Alpha Centauri system. And that is a 3-star system. There's 2 stars close in. Alpha Centauri, I think it's Alpha Centauri A and B. I might be getting that wrong. But the 3rd star is orbiting farther away, and it's kind of orbiting at a distance around the center too. And so it's a third star out there. And that third star is called Proxima Centauri, because at the moment, it is closer to us than the other two. So that protostars, you know, the party's getting going. Everyone's gathering together in the middle. About 10 million years later, that core is now more than 18 million degrees. There's now enough heat and pressure to create thermonuclear fusion. Don't worry, big word. What does that mean? Thermo, it has to do with heat. Thermometer, it's a meter measuring your temperature, right? Thermostat, it's measuring the heat in your house. Nuclear, having to do with the nucleus, the center of an atom. It's actually pretty simple. And fusion is joining together. So you take three kind of simple concepts there, put them together into one big word, and you get to sound smart. Thermonuclear fusion. And here we see that star is really bright there now. Man. All right, so there was all that hydrogen that we talked about. Now it's important. I promised you that it would be, because you're going to take 4 hydrogen atoms, 1, 2, 3, 4, and those are going to be pressed together with that heat and with that pressure. There's just not enough room in there anymore for them to avoid each other, and they get squeezed together, and it forms helium. And there's some waste from this. Not every part of those 4 hydrogen atoms turns into the one helium atom. There's some stuff that gets left off that are called neutrinos, just kind of like junk bits flying off. And the rest of it comes out as energy, which is expressed as heat and light. So if you take 4 atoms and you combine them into one atom, here's Adam Sandler, Adam Savage, Adam Scott, and Adam West, and you were to combine the 4 of them into one new atom, Adam Driver. I thought this was funny. I really hope there's people at home laughing at this, because I kind of took way too long putting this slide together. Anyway, so that's what happens. So let's take our sun. In our own sun right now, every second, 600 million tons of hydrogen combine. Every single second. And every single second that is generating 596 million tons of helium. That's a lot of stuff. But if you are doing the math with me right now, you're like, wait, 600 million minus 596 million, there's 4 million missing. What's going on? Where's the rest of that mass going? Well, as we know from this, not everything turns into helium. Some turns into neutrinos, and the rest is energy in the form of heat and light. And that is what you get when you have a star, right? So here's this animation here that I think shows it pretty well. You see one hydrogen atom going along and another one comes and crashes into it. Okay, so there should be 4 combining, but this illustrates these things collide, and you see this burst of light, and there's heat, and there's energy coming off of it. That's what happens. So you have the inside of the center core of this star where it's super hot. There's a lot of pressure. Hydrogen is combining into helium, and that's pushing outwards, right? It's an explosion. It's a nuclear explosion. Huge atom bomb going off every single second, constantly, for billions of years. And it's pushing outwards. But there's gravity pulling it inwards. So there's this balance that is reached where the gravity is pushing inwards at the same pressure that thermonuclear reaction in the center of the star is pushing outwards, and you have a balance. You have a nice stable star. It stays the same size and stuff like that generally, and that is where our star is at right now. It's at a nice, really gentle, stable point where the fusion pushing out equals the gravity pushing in. I'm going to pop into the Q&A section because I have been neglecting that for a couple of minutes. Okay. Shanna says, oh, I was here the last time you did this class, so you're basically doing the same thing. Yes, we have people here now that weren't with us in the spring. And I don't know about you guys, but every time I cover a subject with you, even if it's something I've covered in the past, I learn something new. I come to some new realization or conclusion, or I'm able to think with it better number of times over studying a piece of information, allows you to understand it better, deeper, and more naturally. All right, so Gerard says the protostar looks like a jellyfish without tentacles. I like that. Shannon's asking, is there such thing as a quadrary system? Yeah, I don't have a picture of that, but my understanding is that those are less common because the more stars you have flying around in there, the greater chance of them colliding. But I do think that there are some out there. Are there 5 or 6 stars in a single system out there? I don't know the answer to that question, but there's definitely a lot with 2, some with 3, I think a few with 4, and that's really cool. All right, people are asking to see the black hole, so we're gonna go forward here. Good. All right. Oh, Evan asked, does the 3-star system collide sometimes? Yep. They do. And at the end, you would have a 2-star system. And a lot of these early protostar systems will have 2, 3, 4 kind of beginning protostars. And there's just a lot of chaos. There's a lot of collisions happening. And even if one protostar forms around the other one, a lot of times the bigger one will eat the smaller one. Kind of cool. Okay. Vet is asking, what kind of star is our sun? You are asking the right question at the right time. So our star is more on the smaller side, which is good. You'll understand why that's good in a little bit. If we were a larger star, we would have some problems. So ours is kind of small to medium sized, which makes it a nice, stable star. The smaller the star is when it forms, the longer its life is going to be. The larger it is, the shorter the life is going to be. And we're going to explain why. We're going to look at why that is. All right. So let's say, here's our sun, right? And it's measured in solar masses. Just how much mass is there in a star? We measure our star as kind of the baseline, as the beginning unit of measurement. So our sun is 1 solar mass, and the life of a sun our size is about 10 billion years. I like that. That's great. Smaller stars, they're called red dwarfs. They can be less than 1/10 the mass of our star. They can last for trillions of years. We've never seen the end of the life of a red dwarf star because our universe isn't old enough for them to have died out. Let's say you get a huge, massive star at the beginning. You don't get a medium or small size one like us. You get a massive one, these blue-white supergiants that are as big, there's as much mass in them as 150 of our own stars. Those things live fast and they die quick. 1 million years and they're done. So we're going to look at the evolution of that. So here we're talking, there's all this hydrogen sitting in this dust cloud. It forms into a protostar. You get thermonuclear fusion going on, but 600 million tons of that hydrogen is turning into helium every single second. Eventually, you're going to run out of fuel. For our star, that happens in about 8 billion, 9 billion years into its life. By the way, for the record, we're about 4.5 billion years into our sun's life. We are right in the middle, man. So we got a long time. We don't need to worry about our sun doing anything crazy for about 4.5 billion years. We're okay. So the sun starts to run out of hydrogen to turn into helium, and the core starts to shrink because there's less of that fusion power pushing it outwards, right? The gravity's starting to win. But as it shrinks, it creates more pressure and more heat. The core now reaches temperatures of more than 100 million degrees. That's a lot of degrees. So the sun says, now for my next trick, I'm running out of hydrogen. No problem. I'm going to take that helium, 3 helium molecules, and combine them together into carbon. And again, when you combine those, you've got you've got some neutrinos that come off, and you've got photons. You've got stuff that comes out as heat and light. This energy, it's basically the same trick as hydrogen into helium. Yeah, hydrogen into helium. It's just the next step up. Then it takes more energy, more heat, more pressure. So there we go. Now that works for a while. That buys it some more, you know, another 100 million years. It'll fuse that helium into carbon, but there is a cost. And you'll see here's this progression of, let's say this is our sun over here in about 4.5 billion years. And its surface temperature is about 5,800 degrees Kelvin. Kelvin is the same size of measurement as Celsius. It's just 5,800 Kelvin is about 5,600 Celsius, I think. That's close. It's close enough. It'll start to expand. It'll start to kind of puff up, okay? And as it puffs up and as it expands, its surface temperature starts to go down. So it gets a little bit bigger and it's down to 5,000 degrees Kelvin on its surface. And it gets even bigger, it's down to 4,500 degrees Kelvin. It's getting bigger and it's getting colder, okay? And then it starts to get a little bit unstable. It starts to burp and it starts to kind of like puff out these outer layers. And here is a sequence of images that shows a red giant doing exactly that. And it kind of like, it's getting bigger and it's starting to run out of energy and it starts to cough and kind of shudder, and these outer layers start puffing away, just kind of floating off from the star. Sometimes it's kind of violent, sometimes it's a little bit less violent, but here we see this, and I'm not sure what length of time these images were taken. I'm going to guess over a period of a few years. Totally guessing there. That is not for certain. But you can see those outer layers puffing away. This is a real image of kind of the aftermath of several puffs of this star getting rid of its outer layers. I don't know if any of you have ever been in a car when it starts to run out of gasoline and it's running fine. And as it starts to run out of gasoline, there's still gasoline, but there's gaps in it. It starts to go put, 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 and you'll feel the car kind of shake. And it's still going for a little bit, but there's this like put, put, and it gets rough, and then it eventually dies. That's what's going on with a star when it's running out of fuel. This is a gorgeous image right here. And you can see in the middle, there's still something shining. There's still the core left after all the outer bits have floated and flown away. And here's what it looks like at the end. You've got this small white star, and it's called a white dwarf. And they're very small. Many white dwarfs are about the size of the planet Earth. That is small. No offense to us, but it's not very big in the terms of, the universe. But they are massive. They have a lot of mass to them. It's 300,000 times heavier than our planet, but it's the same size as our planet. That's crazy to think about. So we have that life cycle for a smaller kind of mid-sized star, right? We turn into a small star like our own. As it starts to get older and loses its hydrogen and it starts combining helium into carbon, it starts to swell into a red giant, and it gets bigger and a little bit colder, and it starts to puff out those outer layers. And then eventually you've got these outer layers float away and you've got the white dwarf left over. So what happens on the other branch? Well, we have the smaller and medium-sized stars are able to fuse hydrogen into helium and then helium into carbon, but that's about where they end off, because they can't get enough pressure and they can't get enough heat in the core to do the next steps. But these more massive stars, these really, really big ones, they can do that. They're going to take that carbon and they're going to fuse that carbon into neon, and that's going to give off light and heat and energy. And then when it starts running out of carbon to fuse into neon, it's going to take that neon and it's going to fuse the neon molecules together to create oxygen, which is really good because we kind of need that. And then it's going to take the oxygen, it's going to form it into silicon. It's going to take silicon, it's going to combine them into iron. That's how the heavier elements are made. That's how oxygen is made. Every molecule of oxygen that you are breathing right now and have ever breathed has all come from the center, the core of a supermassive star in the distant past in the universe. Every piece of iron, right? I've got every piece of metal, anything like that, like my wedding ring. This metal, these molecules were forged in the heart of a supermassive star earlier on in the universe. So that thing about Thor's hammer being, forged in the heart of a dying star. Hey, yeah, they're not joking. That's where all metal came from. Not that Thor's hammer isn't important. All right. Taking a deep breath here, breathing lots of this oxygen that was once in the center of a dying star that then exploded. So Gerard asked, when a red giant burps, it turns into a supernova, right? Okay, thank you for asking that. I wasn't entirely clear before. This is called a nova. The star is going nova. A supernova is different. It's like a nova, but it's super. Pretty technical, right? So you would call this a nova. We're going to stick with that word for now. We're going to cover supernovas in just a minute. All right. So all that's happening inside the core of one of these huge, massive stars. But what happens when it runs out of hydrogen, runs out of helium, runs out of carbon, neon, oxygen, silicon? It can't fuse iron into anything heavier than that. The same thing happens when it runs out of fuel as with what happens to one of the smaller stars. Is the core kind of collapses. It's just no longer able to push outwards, and gravity wins and it pulls it inwards. And in less than half a second, the core of that supermassive star shrinks from the size of the Earth to the size of Manhattan. Like that. Boom. As you can imagine, that generates an insane amount of heat and energy. And that, my friends, is a supernova. These are not gentle burps from an old, middle-aged star. These are explosive ends to super young, super big, super massive stars. They live bright, they burn hot, and they die quickly. Sometimes in like 1 million years, beginning to end. Done. And here's just an illustration that kind of shows that. I'm going to let that run for a second as I take a sip. It's gorgeous. It's absolutely gorgeous and destructive. You would not want to be anywhere in the neighborhood of one of these things. Here's the aftermath of a supernova. And you can see, this is probably many light years in diameter, what's going on here. This thing just blew up. Now you might be saying, wait a second, that looks a lot like the nebula that we were looking at the beginning of the show. Like, don't stars get formed from nebula? But wait, this one exploded and turned into a nebula. Yes, and yes, you're absolutely correct on both counts. One turns in, and that's why it's called a cycle, because a cycle is a sequence of actions that you can count on repeating in the same order, right? The cycle of your day. You wake up, you do a bunch of stuff, and then you go back to sleep. That's the cycle of your day, right? Stars form, they combine a bunch of elements, and then they explode, more or less. And then from that explosion, more stars are able to form and combine into stuff, and they combine stuff, and then they die and they explode. So near the beginning of the universe, 13, 14 billion years ago, there weren't really a lot of small, cool stars. It was a lot of large, supermassive, hot stars that burned bright and died quickly and exploded. And then those clouds turned into new stars, and which died and exploded, which turned into new stars. as stars around each other exploded and all of their stuff started to kind of combine together, those would create stellar nurseries, like two clouds would float together and press together, and a bunch of stars would form between those two clouds in a short period of time, like a nursery, like where you grow a bunch of plants and stuff like that. So it's this cyclic thing. There's a cycle. It goes on repeat. All right. So Gerard asked, didn't the camera that took that image probably destroy or burn? This is not a true image. This is an artist putting together what it probably looked like. So we don't need to worry about that camera. All right, here's another picture of, hey, this is exactly one of the nebulas that we saw at the beginning. Stars are forming or will form, can form inside of that. Here is an image. This was just taken a few months ago. This is a newer image for humankind. And you see, here's an older supernova, and you can see that it exploded and the gas and dust from that have started to kind of disperse out into space in different ways. Fascinating. And to the bottom left, there is a more recent supernova. And you can see it's still kind of new and its stuff is now spreading. This supernova will spread this way. This supernova will spread this way. And eventually those two clouds will start to combine. And where two clouds hit each other, that's a really great place because that gas, which was comfortable, is now starting to get closer to other gas, and it starts combining and they start spinning around each other, and you have new protostars that form in it. So what's left at the center of this thing when it is done exploding? There's going to be something, right? The core shrunk from the size of the Earth to the size of Manhattan. The rest of the star blew away. The core is still there. You have what is called a neutron star, and it's small and it is intense. Here it is. It's about the size of the island of Manhattan, which you can see over there. There's Central Park, and there's downtown, there's uptown. I can see my favorite pizza place in the entire universe in this photo. Oh, now I'm hungry. Thanks, guys. Anyway, there's this neutron star, and there's a lot of energy happening there. There's a lot of really intense magnetism and energy and heat coming off of this thing. If you were to get too close, it would definitely fry you. And there's a lot of gravity, lot of gravity. This is actually not a great artist's showing of a neutron star, because you see these little bits of fire and stuff coming up from the star. That does not happen on a neutron star. There is too much gravity for that to happen. A neutron star is the smoothest object in the entire universe because the gravity is pushing everything together so intensely that nothing can rise up. It gets pushed back down again. So it's getting compressed. And it's the surface. If you were to touch it, you would be dead, but you'd be like, wow, that's very smooth. And I just burned up. So 1 teaspoon of matter from this neutron star weighs 1 billion tons. That's a lot. It's insane. What this is showing here, I like this drawing a bit better because you can see it's super flat, super smooth, not flat, but smooth. And that's more proper. There is some crazy stuff happening at the north and south poles of this. So this thing is spinning really fast, really fast. Some of them spin many times per second, spinning around and around and around. And it's generating these really intense beams of energy, X-ray energy, gamma ray energy that shoot out of the north and south poles of this, shooting out into space. That is really useful because, here's another image. Here's the aftermath of this explosion. You can see these rays of energy shooting out from top and bottom. It looks like some of this stuff is starting to get sucked back into the neutron star there. There's another image there. You can see those jets boom, shooting out. This is a real image. Okay, so this is an artist's image. This is an artist's image. This guy here, that's real, okay? So this thing blew up, and then some of the stuff stuck around and started kind of orbiting this leftover star again. But you can see these rays of just the most magnificent energy coming from the north and south poles. So not only are these neutron stars spinning extremely fast, some of them dozens of times per second, but they're giving off these rays of energy, and they kind of wobble a little bit. They're kind of wobbling back and forth, which means you can use them as kind of a signal light out in the universe. If you're looking for the right type of energy, and one of these rays happens to be pointing at you from, you know, hundreds of millions of light years away or something like that, you can use it as kind of like a lighthouse, a cosmic lighthouse. If you're sailing on your ship and you're not sure where the shore is and the lighthouse is going, and this beam passes you every so often, and you have a map that says, like, you know, there should be a lighthouse over here, and you see the light, you're like, great, I see that lighthouse, I see the beam of light, and I know where I am off of the coast of, you know, Oregon or whatever. Well, you can use that in the universe as well. And we know that there's many neutron stars out there. We can see that flicker of some of them because we happen to be right on the path of that jet of light right there. And we can see, and it kind of flashes to us. There's this flashing of this X-ray energy, and it's extremely reliable. That flash of energy looks the same now as it did 1,000 years ago, as it will in 1,000 years from now, and 1,000,000 years from now. It's very, very dependable. It goes at an exact frequency, and you can use that as kind of a cosmic GPS system. This is a disk that we sent out on the Voyager 1 spacecraft, which was the first human object to leave our solar system. If an alien civilization were to ever discover the spacecraft and look at it, they could look here, and there's enough, you know, if they could decode what we're trying to say here, they could see each of these points here are neutron stars that we know about. And there's code on here showing the frequency with which those neutron stars are blinking to us, some of them many, many times per second. And an alien civilization or humans in the future or whatever, you could take that information, you could look for, find the neutron star that flashes like this, find the neutron star that flashes like this, like this, like this, like this, and you figure out where to position yourself in space so that they're lined up in the right spot, and that is where Earth is. It is cosmic GPS. All right, so what if the exploding star was even bigger than the one that made the neutron star? Well, now you have a black hole. So the gravity of that neutron star was so intense that, like, not even a little blip could push up from the surface. That's why it's so smooth. You add more mass, it gets heavier and heavier, the gravity gets more and more intense. Eventually, it is so heavy that not even light can escape, and that is a black hole. Light goes in, it does not come out. This is an artist showing what a black hole might look like. And it looks a little funny around the side because light, if it gets too close, it gets eaten by the black hole and it never comes out. But light that gets close enough to not get eaten by the black hole, it is going like this, and it passes the black hole, whoosh, and it gets pulled towards the black hole, and then it escapes. And it gets bent. So here is the light from behind the black hole getting bent around it as it's going past it. Here's another artist showing what a black hole might look like. Let's say that there is a disk of material like the rings of Saturn orbiting that black hole and getting pulled in, getting eaten slowly by the black hole, it would generate a disk of light around the equator of that black hole right there. And that disk of light, you know, the material's in there and it's getting closer and closer together and it's moving faster and faster and it's rubbing and that friction is generating heat and light. And that's what we're seeing here. But what about the top and bottom there? Well, remember, if light gets too close, it gets eaten by the black hole. But if it's close enough that it gets bent but not eaten, you are seeing light from the up here and down here. That is that disk behind the black hole. You're seeing behind it right now because light gets weird around black holes. And this, my friend, this is a real picture of an actual black hole. This was released to the world just about a year or two ago. And it is the culmination of a lot of really great scientific work from the astronomical community. This, in my opinion, is one of the historic images of the human race. This is, and always will be, the first picture that we took of a black hole. Okay, I'm gonna pop into the questions here. Alex is asking, do we know how heavy a white dwarf star is? Oh, how do we know? How do we know? Well, for one thing, we can tell how other objects around it are moving and are operating relative to that white dwarf star. If we see that there's a planet orbiting that star at a certain speed, we know that that star needs to be a certain weight, a certain mass, to generate the right kind of gravity to make the planet orbit it like it does. Or you could also look at stars that are nearby it and see how those stars are reacting, just a little changes in how those stars move. And that'll give you a clue as to what the gravity of that white dwarf is. There's a lot of really great science behind it. A lot of science, there's a lot of math and mathematical predictions that they say, well, if my math is correct, we should see this. And then they go to the astronomers look, they're like, yep, we saw that. Great, that matches your estimation there, so we know that this is about right. Or, even more exciting for scientists is, you know, the scientists or mathematicians or whoever, they say, we expect to see this. And they go and look and they see something different. That's one of the most exciting things that happens in science, because it's like, wait, we're gonna learn something new here as soon as we figure this out. So, few things, like a scientist loves confirming something that they knew, but even more so loves confirming that what they thought was correct was incorrect, because we are now pushing into new levels of understanding. Close to the end here, let me check your questions really quick. What would happen if you went into a black hole? Well, Finley, the good news is you would die before you entered the black hole. So I guess that's good news, because if you went in past the black hole, you would be dead anyway. So the process of even just getting close to it, it would, how do I put this delicately? It would tear your body apart. But once you get past it, they don't really know what's on the inside of a black hole. They can predict what might happen with math, but they're not sure of it, because we cannot get any information, not even light, from inside the black hole. So we don't know. We can only guess. And anything that we ever sent in there, if we could send a probe in, we would never get the probe back. We would never get any information from the probe back as soon as it passed that threshold of the black hole. All right. All right, good. Yeah, there's Gerard bringing in the word that I was avoiding, but let's say it. Spaghettification. That is a real technical term. And what happens when something approaches a black hole is the gravity is super, super intense. If you were approaching a black hole feet first, you would start getting close enough that the gravity being exerted on your feet was way more intense than the gravity being exerted on your head, and your feet would be pulled and lengthened out. And then as the rest of your body approached, it would start to kind of lengthen out. And the closer you got, the more intense the gravity would be, and the longer you would turn into a big, long piece of spaghetti. So that's fun. Yep. And Evan is asking, can a planet be absorbed by a black hole? Yeah. And it happens if a planet wanders too close to a black hole. No, it's going to eat it. Just like if a planet wandered too close to our star, it would be eaten. And there probably were planets in our early solar system that did not have a stable orbit, and that got too close to our sun, and the sun ate it. And that planet became fuel. All right. So there's one last kind of supernova. We talked about novas from small and medium-sized stars. We talked about supernovas from these big stars. This is a picture that was taken just a few years ago. And this is 238 million light years away from us. So 238 million years ago, this happened. There's a supernova here, supernova 2006 GY. And the supernova is 100 times more powerful than the average supernova that we have observed. And scientists, they think that this supernova was so intense, the explosion was so energetic, that even the core was blown away, that there is no neutron star left over, there is no black hole, because even the core was blown apart and flung out into space. That's so cool. Okay, so 40 minutes ago, we looked at this slide and there was a lot to learn. Let's look at it again now. We are about 3 minutes over time. I'm just going to take a couple of minutes to wrap it up here because there's no one coming in to start the next webinar for another hour or more. So we start out with this nebula, a clump of gas and dust, and it forms into sometimes a small star, which turns into a red giant, which then has these, it goes nova, not super energetic, but it does kind of puff out and explode a little bit, leaving a white dwarf at the end. And the white dwarf lasts until trillions of years from now. It'll go for a very long time. Or that stuff forms into a large star. It lives fast, it goes hard, it dies quick, turns into a red supergiant, goes supernova, kablooey, scatters these heavy elements like oxygen and iron and silicon and neon all over the universe. And when that stuff forms into new stars, now you can have planets. Now you can actually have planets with, you know, carbon-based life forms like us, and with neon for our signs when we go to see if McDonald's is open, and, you know, iron in order to dig out of the ground, in order to make metal and stuff like that. And what's left over is either a neutron star, or if it was even heavier than that, you have your black hole. What's next? Right, good. This is a chart showing how frequent, how many of each type of star are there. And you've got your white dwarfs down here. You've got your supergiants, your red giants and supergiants up here. And the redder the thing is, the cooler it is. The bluer it is, the hotter it is. So this is hot over here. This is cold over here. This is small on the bottom and big on the top. And you can see there's this line here that almost every single star fits in. And those are called main sequence stars. Most stars in the universe lie along this line right here. But you've got some that are really small like this. You've got some that are super big like this. The universe is fascinating. Our sun is right there, right in the middle. So is Alpha Centauri, our closest neighbor. So we are completely average. Good job, guys. You are not special. That's okay. If our star was special, we probably wouldn't exist right now because it would be too hot, too cold, too energetic, something would go wrong. I'm okay with this. So in our Milky Way galaxy, there's 100 to 300 billion stars. There's 1 to 200 billion galaxies in the universe. So I did some rough calculations and I came up with the phrase that it's like a lot of stars. I'm not wrong. You can check my math on that. It's a lot of stars. You can fight me on that. One last thing we're going to talk about. I know we're 6 minutes over, but what if that protostar doesn't get hot enough to start that fusion of hydrogen into helium? You get what's called a brown dwarf, and this thing might look like a hot Jupiter. I kind of think of you can think of brown dwarf as a hot Jupiter. It never gets that fusion happening in the middle. It's going to stay hot for a while, and it's a little star, but it's not going to do anything super impressive. It's just going to float out there, and it'll slowly cool off. And its core never really reaches 2 million degrees. It might reach 1.5 million degrees, but it doesn't get the fusion. So it will slowly cool down and slowly die. There's a lot of brown dwarfs out there. You can see a brown dwarf would be bigger than Jupiter. Jupiter's not big enough to be a brown dwarf. We are out of time. Thank you for tuning in today. The next space science webinar is going to be on Thursday, and there's a couple different topics that I'm thinking of. We could talk about the search for alien planets, the search for planets outside of our own solar system. That's kind of what I'm leaning towards. If that's something that you're interested in, say so in the Q&A section. I'm going to end the class here, but I'm going to hang around in the Q&A section for a few minutes to answer some more from you guys, because there's way more questions than I was able to answer on camera here. Thank you so much for tuning in and for your interest, and I will see you guys on Thursday. Coming up this afternoon at 1:15. Oakley, what's our last class for the day? Do you have that sheet with you?
Yes, I do. It'll be book club with Quinn.
Book club with Quinn. Oh, tune in for that, guys. It's going to be great. I'll see you later. Oh, helmet on.